Hey, welcome back. This is Charlie, and this is the last video, the third part in Chapter 1. We're going to talk about maps, cartography, and tools geographers use that aren't maps. So a map definition: generalized view of an area as seen from above and with reduced size and detail. So a map is a generalized view of an area. It doesn't have all the details, obviously, that reality does. Otherwise, it would be impossible to see anything. Maps usually are printed as if you're flying directly above the area that you're looking at. Obviously, reduced size, that gets into scale, and I'll talk about that in a minute. Cartography is the science and art of map making. Some of the common elements that maps have: most maps have a title, so you know what the map is about. A north arrow, so you know which end is up. The symbols: what does this blue color mean? What's the red color mean? Those are all explained in the legend. What's a red line? What's this black line mean? Those are all explained in the legend. A scale bar or ratio tells you what the relationship of the size of the map is to the size of the place that the map is of. So scale. Scale is the ratio of the size on the map to the size on the ground. There's three ways of expressing scale. Representative fraction, like 1 to 24,000. So 1 inch on the map is 24,000 inches on the ground, or 1 foot is 24,000 feet. The numbers, or rather the units on both sides of the colon, have to be the same. So it's 1 inch to 24,000 inches, or 1 foot to 24,000 feet. Both sides are in the same units. There's a graphic scale or a bar scale. Those are great if you're going to Xerox or copy the map and blow it up or reduce it, because the scale bar grows and shrinks the same amount as the map. If you had a representative fraction map, an RF map, that was printed at 1 to 24,000, but then you blew it up, it wouldn't be 1 to 24,000 anymore. So for maps that are going to be enlarged or reduced in size, graphic scales, bar scales, very, very helpful. And you can also have a written scale, and a written scale has different but common units. So saying a written scale would be 1 inch equals 1 mile. So the units are different. It's not 1 inch equals this many inches, it's 1 inch equals 1 mile. Oh, so a written scale would be 1 inch equals 1 mile, and then a representative fraction would be 1 to 63,360. Those would be two different ways of expressing the same map scale. As a written scale, it would be 1 inch equals 1 mile. As a representative fraction, it would be 1 to 63,360. So you can also talk about map scales as being small scale or large scale maps. Small scale maps, let me pick up the pointer again. Small scale maps have small detail of a large area. Large scale maps have a lot of detail of a small area. So this is, as it was printed at some point, 1 to 500,000 scale, where 1 inch equals 8 miles. This is 1 to 24,000, 1 inch equals 2,000 feet. So this map, and there's no such thing as the best map scale, it's just what do you want the map to show? If you want it to show the relationship between downtown LA, Beverly Hills, and Long Beach, you'd use this map. If you were wondering what's in walking distance from the Transamerica Center or the Convention Center, you might want to use this map because it's a larger scale. Larger scale has more detail of a small area. Oh yeah, so in this day and age, most of you are used to using Google Earth. When you zoom in, that's larger scale. When you zoom out so you can see the entire US, that would be small scale. If you zoom into your town, large scale. If you zoom out to see the whole globe, small scale. One way of thinking of it is to look at the representative fractions. 1 over 500,000, 1 over 24,000. So the 1 over 500,000 seems like it's bigger, but it's not. It's 1/500,000th. So you just got to ask yourself, would you rather have 1/500,000th of Bill Gates' money or 1/24,000th of Bill Gates' money? I'd rather have 1/24,000th. There's a video on map projections. I'm going to put the link to that in the comments, or not the comments. Well, I'll put it in the comments as well. I'll put it in the comments and I'll put it in your lecture notes. so that you can watch it on your own. In fact, all these videos, if you click through to the lecture slides, the videos are embedded in the slides, and that's another way to watch them. So map projections, talking about map projections, something's going to get jacked up. With any map projection, either the size or the shape is going to get messed up, because Earth is a sphere and maps are flat, and it's impossible to go from a sphere to a flat shape without distortion. Right. So this isn't mine. I stole this shamelessly from the internet. This board geography instructor took a orange, used a Sharpie to draw a map on it, and then peeled the orange in a homosign projection. And you can see across the poles, right, like on this orange, the lines of longitude are the sections, and they all come together at the North Pole. All the lines of longitude come together at the North Pole on a globe. But on a map, and on this map, they're not. There's these big gaps because all of that fit together when it was on a sphere, but now that it's on a plane, you're going to have to stretch it out, and that's going to cause distortion because whatever was here is going to get stretched out and get bigger. So, map projections are how we transform a spherical shape to a flat shape or vice versa. All maps have some type of distortion, either the size or the shape. Sometimes both are distorted a little bit, and you can make a compromise projection. You can have an equal area map in which the sizes of places are accurate, or you can have a true shape, in which case the shapes of the countries will be correct, but the sizes will be distorted. The Mercator projection, a very, very common conformal or true shape projection. This is a Mercator projection. Again, remember that all the lines of longitude converge at the North Pole. So on a globe, all of these vertical lines come together to a dot. So to make the Mercator projection, they've taken the dot at the North Pole and they've had to stretch it out so it's as long as the equator. So along the equator, it's pretty accurate. In fact, these should be triangles, right? Going from the 60th parallel to the 90th parallel. This should be a parallel because all these lines are coming together at the North Pole, but they're not. So there's enormous distortion. The shapes are correct, but not the size. So you can look at Greenland and Australia. You can look at Africa. You can look at Russia and the United States. So the shapes are correct, but the sizes aren't. This is the Mercator map. It's a great map to use if you want to emphasize how big and scary Greenland is or Russia is, or if you wanted to pretend that Africa was small. So this map is the exact same scale as this map. This is an equal area map. So Australia is actually 3 times bigger than Greenland. But on a Mercator map, Greenland looks way, way bigger. Canada looks huge. Everything at high latitudes gets way bigger. Everything by the equator gets way smaller. So this is an equal, an accurate shape map. This is an equal area map. And again, the areas are accurate. So Greenland gets small, Russia gets small, Africa gets big. Much better map to use, especially if you're going to show things like population, that the areas should be equal. Oh, these are Tissot's indicatrices. Tissot is a French mathematician who thought, what would be great would be if you could plop the same shape all over a globe and then use the changes in that shape to demonstrate what the distortions of that projection are. So if you took a globe and you put dots on it that were all this size, and then you plotted that globe on a Mercator projection, you can see there's still circles, but they're much, much bigger. And in fact, if we had circles across here, they'd be even bigger yet. So the Mercator is great if you want to display the shapes of places, but not the sizes. This is Eckert 4. This is an equal area projection. You can see the higher latitude, they're not circles anymore. They're getting all skewed out. They're like these weird ovals because the shape is distorted, but not the size. The size of all these dots would be exactly the same, and you can see exactly how much distortion and what type of distortion you have using Tissot's indicatrices. A geographic joke. Bad map projection number 358. Oops, all South Americas. Another geographic joke. This is Argentina. Everything else is Argentina. Here we've got another comparison of the Mercator with the accurate shapes and the Eckert 4 with accurate sizes. Some maps have isolines. ISO means the same. That's one of those words. You should probably write that down. ISO means the same. Lines that represent a given value. Contour lines are lines of equal elevation, very common on hiking maps. Isobars are lines of equal pressure, another type of isoline. Types of maps, topographic. You could have a topographic map. Those are going to have contour lines to tell you how high places are on that map above sea level. This is a topographic map of Yosemite, where the lines are close together. These are contour lines, lines of equal elevation. So if you walked along this contour line, you would be exactly the same of elevation above sea level the whole time. When they're far apart, that means that there isn't a lot of vertical change, so it's flat. Like right here, you can see from all the way from like here across the other side of the meadow, it's totally flat. Here, the lines are so close together that they look solid, and that's a cliff. So cliff, cliff. The spacing of the contour lines will tell you how steep it is. The closer they are together, the steeper that place is. So this is one type of map. This is a topographic map. This is a map showing slope, how steep the slopes are. When you look through it, I would go back and forth because they're showing the same area of Yosemite National Park. You could compare how the steep places look on the topographic map to how those same steep places look in a slope map. This is a geologic map of, again, the same exact place in Yosemite, showing what the subsurface geology is. Another geoscience tool is the Global Positioning System, or GPS. The GPS system tells you where you are by listening to the satellites. One satellite will tell you if you're only listening to one satellite, you're someplace on the surface of a sphere that's equidistant from that satellite. Yeah, I should probably talk about GPS. So GPS is super fascinating because part of it is very sophisticated and part of it is very simple. The sophisticated part is they're using atomic clocks with billionth of a second precision. The simple part is they are just screaming their location 24/7. So your GPS unit on your phone is listening to the satellites, and the satellite screams out, "Here's where I am and here's what time it is." Your phone picks up that signal and says, "Oh, the satellite says it was noon, but it's really noon and 1 second now when I'm getting the signal." And then it calculates out based on the speed of light. 300,000 kilometers per second is the speed of light. So if it took 1 second for that message to reach you, the sender is 1 second away, and 1 second at the speed of light is 300,000 kilometers. So by timing how long it takes the signal to reach you from each of the satellites, it figures out how far away you are from each of those satellites. The satellites knew where they were when they broadcast that signal. So the computer on the chip figures out your location just doing division. Like, it took this many seconds to arrive here, so you're this far away. To get a 3D fix, you need 3 satellites. And in a couple minutes, a couple seconds, most of the time, they can tell you exactly where you are on Earth within a couple feet, which is phenomenal. Another modern geoscience tool, remote sensing. I've put up a couple links to remote sensing sites. The most recent example would be the fire maps that we've been seeing. So those are all remote sensing. They're all passive. So there's a satellite, it's orbiting Earth a bunch of times a day, and it's just receiving energy that Earth is emitting. And that's called passive remote sensing. Active remote sensing is when you send energy out and measure how much of it comes back. So our eyeballs are passive sensors. They're not like sending out rays and then measuring how much comes back. A flash photography in a dark room would be active sensing, active remote sensing, because you're sending out energy and you're measuring how much of it comes back. Radar, active remote sensing. You're sending out radio waves and you're measuring the strength of the returns. LiDAR, one of the more important ones that I'll talk about, is using light lasers to measure distances from a known location. LiDAR uses laser beams to measure distances, so they can put a LiDAR unit in an airplane, fly over the surface of Earth, and develop very quickly a very accurate, very precise three-dimensional model of that surface that they flew over. This would just be passive remote sensing. We're just looking at visible energy, looking at storm runoff entering the ocean. So, LiDAR. You can put LiDAR in an airplane, fly over the jungle. One of the cool things about LiDAR is it's sending out literally millions of laser beams, measuring how long it takes to come back. And then they are able to filter out the returns. So if you imagine if you're flying over the jungle in an airplane, bouncing a laser off the surface, some of the laser beams would bounce off of the trees and bounce off. Some of them would make it through the trees to the ground and then come back. And so this is LiDAR mapping of an area in Central America that if we flew over it, we'd probably just see trees. But by using LiDAR, they can strip out the trees and you can see the bare ground underneath. Or using LiDAR, you could make a three-dimensional map of the forest because the LiDAR system knows, oh, this is the first return, so it's off the top of a tree. I sent it at the same direction, but this is the bare ground return. So then you could color code the LiDAR data by the distance from the receiving unit. This is New England. Flying over New England, much of New England was cleared by invading colonists, and they have abandoned those farms, abandoned those fields, and the forest has grown back. So just looking at it, it looks like just forest. But looking at the LiDAR, looking at the bare ground return, you can see these are all stone walls that are the limits of different farmers' fields. And all of that totally invisible to the naked eye. But if you're using LiDAR, you can strip out the vegetation. So another example, this is the Oso slide. This was up in Washington State. Here's the first return, so you can see the trees, you can see the forest. Here's the bare ground return. So with the first return, you can really see the difference between the slide and the forest around it. So if you wanted to map out this Oso slide, I would say, yeah, you really should use the first return. But I was really surprised when I saw the bare ground return for the larger region, and I realized, oh, that's a landslide. That's a landslide. Here's a previous landslide. Here is another landslide. The whole area is really, really hazardous and prone to landslides. But you can't see it because the vegetation has grown back. So in a couple of years, this forest will regrow and it'll look just like the rest of the forest. But by using LiDAR, you can virtually strip out the vegetation and get an idea what's under the vegetation. Close-up view. In fact, on the slide at the full res data, you can actually pick out individual trees. We could measure how wide they are, how long those trees were. Those are all trees that fell down as a result of this landslide. And then the bare ground return, you can see there's weird artifacts like this is a road. Here's another road. It's either a stream or a road. And now it's just all it's bare ground. There's no vegetation being shown. It's the bare ground return. So now you have an idea what the whole surface of the ground looks like. This was a fun map I did of Sacramento using LiDAR data. So it's color-coded based on elevation above sea level. You can see here's the current American River, and here you can see going through what is now downtown is where the American River used to run. The streets you can see are lower in elevation. There's no buildings on this, which is really interesting. And then there's weird things like ramps, like there's a bridge here, but the LiDAR data, they stripped out the bridge, so you get the ramp leading up, and then nothing going over the top. Same thing over here. Here's a ramp with dirt, so there's a bridge. There's got to be a bridge there. Different color scheme, sometimes doing the same map using a different color scheme, different details stand out. This was a map I did of Yosemite Valley. And what I did was looked at the bare ground return, and I said, okay, take the elevation of the first return and subtract from it the bare ground return, and the difference would be the trees. So I was able to then do a shaded relief with the bare ground and have it color-coded by tree height. And then here's just the bare ground return, which affords you a really good view of the Merced River running through the park. You can also see abandoned channels where the river used to run. So this is the bare ground return of Yosemite. And this is literally a map of like every tree in Yosemite Valley because of LiDAR data. Bare ground return again of Yosemite Valley. GIS, Geographic Information Systems, are probably one of the most important geoscience tools. In fact, these maps were made using geographic information systems. Geographic information systems are super powerful because they combine spatial data with attribute data. The spatial data is about where it is, latitude, longitude, height above sea level. Attribute data, what is it? So when I first started taking geography classes, in fact, in grad school, the GIS systems were still using command line interface where you'd have to do programming, writing out text commands. Shortly after that, they came out with the first GISs that had a graphic user interface where you just click buttons to do stuff that made it much more accessible. And now we use GIS systems on a daily basis without even thinking about it. If you use Google Maps, you're using a GIS system. Google Maps are a front end, a user-friendly front end to a very sophisticated GIS backend. The shipping companies use GIS systems to route packages to figure out either the shortest distance or the shortest amount of time to deliver all these packages. This is a GIS model, and a model is a simplified version of the world. This was a U.S. Geologic Survey model to predict wildfires that would produce mudflow or landslides. So one of the problems is when you get a big wildfire, it burns all the vegetation. So in the fall, when it rains, there's nothing to soak up the water, and you tend to get big mudslides, big landslides as a result of forest fires. So this was a model that the USGS developed to try to predict regions that would have landslides as a result of wildfires. So they take an elevation layer, and from that they can compute how steep the slopes are. The steeper the slope, the greater the chance. They can look how much upstream has burned. So the more bare ground there is, the greater the danger for a landslide. Clay, when it gets wet, is really slippery. So the more clay there is in the soil, the more slippery the soil will get when it gets wet. And then rainfall upstream. The more rainfall you'd expect to get in a storm, the greater the hazard. So they can put all these together. They can weight them, like maybe the clay is more important or less important. So it's all done with numbers. It's all done with calculating things automatically using computers. And the end result is this, and this were all high landslide risk. And then the yellow areas are low landslide risk, probably because they're smaller, not as steep, less clay content, all of those things. And then finally, geovisualization, it's kind of a map. In fact, that would be my definition. If I was going to write the definition for geovisualization, I would say it's kind of a map. You're showing geographic things. You're not using a map per se. Google Maps, Google Earth, both of those are excellent examples of geovisualization. So is it a map? Well, maps are simplified versions of an area as seen from above. So we're above, but we're looking at the side. So I'm not going to give you a full-on map. It's geovisualization. This is Mount Rainier, and it's a study if once Mount Rainier erupts, the lava and ash is going to melt a lot of the ice and snow, and you're going to get these mud flows that are going to move downhill. And so it's telling you how long you've got between the eruption and the mud flow. 10 minutes, 15 minutes, 20, 25 minutes. So this is an example of geovisualization. It was put together using a GIS system to calculate out how long it would take the flow to reach different areas. Like here, it has to go along the long way. So it's going to hit Welch's from this side in half an hour. It's going to hit Welch's from this side in over an hour and 15 minutes because it has to go around the long way. But looking at it, it's clear where the hazard areas are, and it's clear how long you've got to get out of town before the mud flow hits. So geovisualization, it's like a map. It's just not exactly a map. And then Google Earth, this is looking at the retreat of one of the glaciers in Greenland. I think this is the Petermann Glacier. It's one of the faster retreating glaciers, showing how far down the ice had come during different years. And that's it for the first chapter. You've made it all the way through the third video for the first chapter in Introduction to Physical Geography. I hope you enjoyed that. If you have any questions, if you have any suggestions on things I could do better, please, please, please let me know. Thank you very much, and I hope you enjoy the chapter.